In this section, we'll look at determinants, and not just determinants of 2x2s, but of any size, and how they connect to a matrix being invertible. So here are two matrices, and then we're just going to find the determinant, and let me just tell you that the determinant of a 2x2 is AD minus BC. So in this case, it's 3 times 6 minus 4 times 5. So this is 18 minus 20, so the determinant is -2. And if we remember, the formula for the A inverse is 1 over AD minus BC times dA negative B negative C. So the point of that is that it has an inverse. The second one, the determinant of B, is 3 times 4 minus 2 times 6. So that's 12 minus 12, which is 0. And if I put it into the formula, I have 1 over 0 times the matrix, and this is undefined. So B is not invertible. We also say that B is singular. So there is what we call a shortcut method for finding the 3x3. We haven't looked at the long way yet, but so this is considered a shortcut, even though it may not seem like it. And I'm just going to go through this with an example. These absolute value bars are another way to denote the determinant. So when we do the determinant of a 3x3, I rewrite the first two columns. So I'm going to rewrite these first two columns, and you multiply through diagonals. So if I do that one, I would get 12. If I do this one, I get 10. And if I do this one, I get 0. The other diagonals, so this way, I get -6. This way, I get 0. And this way, I have 40. And then notice the ones at the bottom are positive, the ones at the top need to be negated. So I can think of this as -12 minus 10 minus 0 plus -6 plus 0 plus 40. So all of those negatives, so -12, -22, -28 plus 40 gives me 12. So the determinant of that matrix is 12. And because the determinant is not 0, I know that matrix has an inverse. So I mentioned that previous method was a shortcut. Here's the, quote, longer way to do the determinant. And I'm not going to spend a whole lot of time going over this formal definition. This method is called cofactor expansion, and here's the definition of a cofactor. And I'll show you in the example what part that actually means. And then some people use the signs of cofactors. I don't, because they are implied in the definition. So again, we'll go through an example. This definition is very formal. You will not be asked to regurgitate this method, but you will be expected to be able to perform the method. So in exercise 3, it gives us a matrix. I want to compute the determinant of A using the formula presented. So I'm going to do cofactor expansion across the first row. So that's the method we're using. Just highlight that we are doing this cofactor expansion about the first row. So it's going to be 0 times some determinant minus 4 times some determinant plus 1 times some determinant. All right, so the way we find the determinant that goes in each of these spots, you cross out the row and the column corresponding to that 0, and the numbers that are left are what go in here. So I have -3, 0, 3, 1. I'm going to do the same thing with the 4. Cross off those, and the 4 numbers I'm left with are 5, 0, 2, 1. And then with the 1, the ones that are left are 5, negative 3, 2, 3. This term is 0. Then I have minus 4, and the determinant of a 2 by would be 5 times 1, so 5 minus 2 times 0 is 0. And then plus 1, and the determinant of the 2 by 2 is 5 times 3, or 15, minus a negative 6. Here I have negative 4 times 5, I have negative 20, plus, and then 1 times 5 plus 6, so plus 21. So this is equal to 1. So the determinant of this matrix is 1. Again, it's not 0, so the matrix is invertible. So I want to emphasize here where the signs came from, and what I mean by that are the fact that this is positive, negative, positive. So there's two ways you can see where that comes from. One is from the signs of the cofactors. The first one's positive, second one is negative, if you're starting at 1, 1. The other way to think about this is this one is positive because 0 is in the 1, 1 position, so it's negative 1 to the 1 plus 1 because it's in the 1, 1 position. And 1 plus 1 is 2, negative 1 squared is positive. Then the 4, so this 4 is in the row 1, column 2 position. So negative 1 raised to the 1 plus 2 is negative 1 to the third, which is negative. So that's why that 4 is negative. And then to think about why this one is positive, that is in the 2, 2 position. So it's negative 1 to the 2 plus 2, which is negative 1 to the fourth, which is positive. So that's where those signs can come from. One of the great things about cofactor expansion is that it can be done about any row or column. So I'm going to find the determinant using the second row and the third column. So let's first start with the second row. So let's think about negative 1. The 5 is in the row 2, column 1, times 5 times the determinant of what's left over if I cross them out. And keep going. So I have plus negative 1. The negative 3 is in the row 2, column 2, so 2 plus 2 times the negative 3 times the determinant of all the stuff that's left. So 0, 1, 2, 1. And then working this out, notice this is a negative 5 times 4 minus 3 plus negative 3 times 0 minus 2 minus 0. So negative 5 times 1, and then negative 3 times negative 2 is a plus 6, which equals 1. So why don't you guys try doing the determinant around the third column and then compare it to my solution. So this cofactor method works for any size matrix. So here's an example of a 4x4. Notice that we can use any row or column we want, so be smart about it. So pick the one with the most zeros. So I notice that row 3 has the most zeros. That means it's going to be less computation. So the determinant would be negative 1 to the 3 plus 1, because I'm looking at the third row, first column. And then if I cross off the third row and first column, I'm left with 0, 0, 5, 7, 2, negative 5, 3, 1, 7. And notice that all the other values in row 3 are 0, so I don't need to, technically this would be plus 0, plus 0, plus 0. At this point, you can use the shortcut for the 3 by 3, or you can use cofactor expansion again. So I'm just going to use cofactor expansion again. So I have 3 times, and if I look at row 1, I'm going to have 0 plus 0, and then negative 1 to the, that is in row 1, column 3, times 5 times the determinant of what's left, so 7, 2, 3, 1. So I have 3 times negative 1 to the 4th is positive, so times 5 times 7 minus 6, which is 1, so 3 times 5 is 15. So the determinant of this matrix is 15. I'm going to do the same thing. I have a 4 by 4 matrix. I'm going to use cofactor expansion. I'm going to be smart about it. I'm going to choose column 4 because it's mainly zeros, so it would be 0 plus 0 plus 0 plus negative 1 to the 4 plus 4 power times negative 3 times the determinant of the stuff that is left when you cross off that row and column. 3, 0, 0, 7, negative 2, 0, 2, 6, 3. Continuing, negative 1 to the 4 plus 4 is positive, so I have a negative 3 times, if I do cofactor expansion around the first row, I'm going to get negative 1 to the 1 plus 1 times 3 times the determinant of the stuff that's left. Negative 2, 0, 6, 3. So I have negative 3 times 3, since that negative 1 is a positive, negative 1 squared is positive, times negative 6 minus 0. So I have negative 3 times negative 6, so I get 54. So I just want to point out, this next theorem will also stated that 3 times negative 2 times 3 times negative 3 is also 54. This is a special type of matrix we've seen before, so because all of these are zeros, this is considered a lower triangular matrix, and the determinant of a triangular matrix, whether it's lower or upper, will always be the product of the diagonals. So we could do this easier if you recognize that. And that's what this next theorem just says. If A is triangular, then the determinant is a product of the entries on the main diagonal. So recognize that this is a upper triangular because all the values below the diagonal are 0. So the determinant of this is 1 times 3 times 5, or 15.